Your office looks fantastic.
Yeah. Professor Kalyan, we have 2 minutes to go. It's 10:28.
Yeah. So whenever you tell me, I will share.
Yeah. I'll tell you.
Yes.
So good morning, everyone, and good afternoon and good evening at many places. Welcome to this fifth session of ICSFA 2020. And this morning we have 4 speakers with us in this session. The first speaker is Professor Kalyan Chakraborty from Kerala School of Mathematics, India. I'll request Professor Kalyan to start his talk.
Thank you so much, Professor Ali, and it's a real pleasure. So thank you so much, Professor Ali, and it's a real pleasure to be here. Unfortunately, due to this pandemic situation, we are stationed at our own places, can't meet physically. But it's really overwhelming that the way you have organized this conference, not letting it go in such a grand fashion. So thank you, congratulations to you and your team there at Babu Varanasi University. So let me start my talk, and let me, in the beginning itself, tell that this partitions is a new area that I have entered. It's a joint work that I would like to report with Dr. Shigeru, who is a postdoc at Harishchandra Research Institute in Allahabad. And we were discussing about certain modular forms, quotients and all. Then he told us this kind of a problem is there, and we did some work. So I would like to report on that. So excuse me if as I told you that I'm a novice in the area of partition functions. I know there are quite a few experts who are there in the audience. So that's the beginning. That's how I want to begin with. Appears not going down. Just a second. be able to share again. Just a little bit of technical. I'll just share again, Dr. Ali, with some technical things coming up.
It's okay.
Yeah, thanks, Akhilesh. Yeah, so the title of my talk is certain eta quotients and irregular overpartitions. I will come to this term as I progress. What Akhilesh? I don't know what is happening. Suddenly it was just going, but now. Yeah, so this is the outline of my talk. I'll just go a little bit with partition function and then go ahead with some conjecture of Ramanujan and then some basic modular form which will be used to prove the result. And then I'll go to what is called the irregular overpartition. I don't know, as soon as someone is entering, it's not going. Hmm? I think, Dr. Ari, as soon as somebody is entering, this slide is getting stopped. So it's not moving. Yeah, so let's move on. Akhilesh is there next to me. So a partition of a positive integer n, as all of you know who must be attending, is a non-increasing sequence of positive integers whose sum non-increasing, whose sum is n. And this function is denoted by Pn, which counts the total number of partitions of a given n. For example, if you want to calculate the number, the P5, then you will have this 7 members in P5, and so P5 is equal to 7. This is the way non-increasing sequence of positive integers to sum is 7. So there are 7 ways you can write it, and we put P0 as 1 for due to convenience, for our convenience, and this circle thing are called the parts of a partition. So this Pn, if you want to know how fast it grows, so that's a good problem to think of, and you can see that how fast it grows. It's like if you look at 108, so that's big number, which is that red line that you will have it, but still not that big. Like yesterday, there was a fantastic talk by Professor Kannan Sondarajan, and he was comparing this Pn with with the symmetric group of order n and characters and other things. So it doesn't grow as big as fast as this factorial n of symmetric group of order n, but still it's pretty big. So generating function of Pn, people have studied over 740. It was a question put by Node to Euler, and one of his questions was in how many ways can positive integer n be represented as a sum of positive integers. Yeah, so that's what is happening as soon as someone is entering. Then it will go ahead. Yeah, so this is Euler's answer was that if you are generating function, that p n q power n is 1 over 1 minus q to the power n equals to 1 to infinity when you have this mod q is less than 1. So if you look at this product and expand it a little bit, so it will look like what you see in the last sum, that is this n1, n2, n3, which will be going from 0 to infinity, and q to the power 1 times n1 plus 2 times n2 plus 3 times n3, etc. Again, so I think we have to bear with it, Dr. Ali, because every time someone is entering, the slide doesn't move forward. We have to again go and share it afresh. So suppose your n is like, that's the partition, you think 1 times n1 plus 2 times n2 and k times nk. Then here n just denotes the number of times that ni is I appears in a particular partition of n. There's a notation that one is fixing. For example, 3 plus 2 plus 1 plus 1, we can write as 1, 3 times 2 1 times 3 1 times 0, etc. So again, we have to go out there. That's the problem. What is the problem? Yeah, so clearly q power n appears in the series expansion of the product exactly those many times as there are partitions of n. So Ramanujan congruences, famous congruences in 1919, Ramanujan announced that he had found 3 simple congruences satisfied by Pn. So congruences are very nice properties that number theorists and others to study. So namely, he found that 5n plus 4, 7n plus 5n plus 4 is congruent to 0 mod 5. 5 divides that number, and 7 times n plus 5 is divisible by 7. 11 times n plus 6 is divisible by 11. The number of partitions of that particular n. So he proved the first 2 congruences and derived the following. This is called Q series identities. That P of using this Q series identities. He proved that you can see that these are very well known for P 5n plus 4 Q power n. So it is 1 minus Q. That's the standard. I think 5 times, and similarly for 7. So he made a remarkable observation also. He remarked that there are no simple congruences for Pn whose moduli involve primes other than those 3 primes that we had talked about, 5, 7, and 11. Sorry about this technical thing that is cropping up, but we have no other way to solve it right now. We have to go every time and share it again whenever somebody enters. So this is the following result, which is kind of justifies Ramanujan's claim. This is by Algren and Boylan in 2003, that if L is a prime and beta is between 0 and L, an integer for which this P of Ln plus B is congruent to 0 mod L, which Ramanujan was taking up. For every non-negative integer n, then L and B has only these choices, nothing else. So you can see L is 5, 7, and 11. So that was kind of confirming the remark that Ramanujan had made. So there are other congruences. One can, which is different from what Ramanujan was looking up. Like you can look at this one, this 11 power 3 into 13 times n plus 237. You want to count the partition function and see whether there is any congruence property satisfied by that number. So it is congruent to 0 mod 13. So 13 is another prime, which in addition to the study of Ramanujan type congruences, of course, it is natural to consider the distribution of the partition function modulo some some positive integers, not only just prime. In a significant contribution, as Ken Ono, in a paper in 2000, he developed aspects of periodic theory of half integral weight modular form and used these to prove the existence of infinite families of partition congruences modulo every prime L bigger than or equal to 5. So used, so this is the time when this modular form came into the picture, and Ken Ono kind of combined that theory using the arithmetic of modular forms to solve certain problem in the theory of partition functions. So let us define for a positive integer n. So it's the parity conjecture of Parkin and Shanks. Let n be a positive integer and r is between 0 to m. We define this del r mf. It's kind of a density thing that we count all the numbers up to x, so that the Pn is congruent to r mod m, and we divided by this x. That's the bound that we are looking at. So it predicts, this well-known conjecture predicts that the values of Pn are evenly distributed modulo 2. So this is the conjecture of Parkin and Shanks. It says that as x tends to infinity, this del r 2x, so mod 2, is half. This is still a conjecture, and not much that we know that it is known about it. And then this one, it is close. Now this is distribution of this partition function. So this is the work of Gordon and Ono, and they proved that for any fixed positive integer k, the number of partitions of n into distinct parts is divisible by 2 power k for all n. So that is this PDN, which denotes the number of partitions of n into distinct parts. Then as you tend your x to infinity and set n up to x, and look at this PDN modulo this 2 power k, it's 1. So Catherine Riemann and Lovejoy showed that this is also true for the number of overpartition pairs. I'll come into what are overpartitions. So that was also a remarkable work which Riemann and Lovejoy did show. And Lin did the same work for the number of overpartition pairs into odd parts. So we will come into that one. So let's give quickly to modular forms. So modular forms are very nice functions on the upper half plane, which has lots of symmetries. And this upper half plane, this SL2G works on that one. And these functions, with respect to this upper half plane, behaves in a very nice way, which gives rise to a lot of symmetry. So these are some subgroups of SL2G, which are of importance, so-called congruent subgroups that one looks at in. This is gamma n, gamma naught n, and gamma 1 n. And we know that gamma n, these are the subgroups in SL2G, which are of arithmetic importance. And that's why people study this modular forms with respect to these congruent subgroups. So let's go on. So this modular forms, as I told you, that of level n and weight k is weight L is here a holomorphic function, and integer weight L and level n. N means that the group that one is looking at, this gamma n, with respect to gamma, if the following things hold, this nice symmetric, this gives rise to a symmetry. This L is called the weight, and this n is called the level, with respect to which this function is a modular form. And then it has a nice Fourier expansion, which is of great importance, that a gamma n qn, this is the level to the power n. The qn is this e power 2 pi I z over n. This is quite well known. All of you will be familiar with basic modular form theory, and this is a very, very fascinating area to work in modular forms and elliptic curves and all. So then I'll go to what is called eta quotient. You remember the title, there was this eta quotient thing. So it's a, so Dedekind eta function is defined by this q to the power 1 over 24, 1 minus q to the power n equals 1 to infinity. And q already you have defined e power 2 pi I z. But z is in the upper half plane. So this is a familiar Dedekind eta function. People have extensively studied this function. And now a function f is called the eta quotient. Eta quotient if it is of the form this. So eta delta z to the power r of r sub delta. So here n is a positive integer and this r delta is also an integer. So this is what is called, so this eta, it's through this Dedekind eta function. This function f is called an eta quotient. You cannot go again. So this modularity, now people wanted to see that whether it is a modular form, and if it is a modular form, what is the level and what is the weight, etc. And so the theorem of Gordon, Hughes, Newman, and Lyozat, it tells that if you consider the zeta quotient, such that if you take your weight is half r delta, delta dividing all these that capital M, the level one is talking about, and this delta r delta satisfies modulo 24, it's divisible by 24, and so these conditions, and n over delta r delta is congruent to 0 mod 24, so 24 divides this this number, then f is satisfies this property, which is required for to become the modularity property, what is called, for every ABCD in gamma naught n, where this character chi d is the usual symbol. Again, it will not go. And the order of vanishing of the f at the cusp is a rational number c over d is this, where c, so one knows the order of the vanishing also, one knows the character, one knows the level, and the weight also for this form. So this it is one, so this is well known. And now a little bit about Heike operators, very quick thing. So you have this modular form, which is of weight k, level n, as character chi, eventipus. Then the Heike operators will be defined by this class operator, which is you have this coefficient. This coefficient will change it like this. They're very explicit. One can calculate this eigenvalues and of this thing. So we call it a Hecke eigenform if it's an eigenform with respect to this operator Tm. Tp. So in particular, if f equal to p is a prime, then it takes a very nice shape, and it's like a of pn. A of pn is simply the coefficient you see here. This chi is well known, p power l minus 1 a n over p, q power n. So this coefficient changes like that when you apply this Hecke operator on this particular form f. It's called a Hecke eigenform. If for every m bigger than or equal to 2, there exists a complex number lambda m, for which f of Tm is lambda m f of z. Okay, so this is where it forms for every t, every Tm. Then you call such a form Hecke eigenform. Now I go quickly to the what is called Irregular Partition, work of Potil and Lovejoy in 2004, that they defined this one and studied quite a few properties, nice properties of this particular partition function. There's various generalization of partition function is there, and this is one of the popular ones. So what is the overpartition of n? N is the partition of n, which is with the first occurrence of number may be overlined. I'll just give you what is this overpartition of 4. So there are 14. This is the usual partition. Then the first occurrence of the number is overlined. So you count that there is p bar of 4 is 14. So this is people have studied over the years. So starting from the work of Rogers and McMahon, Gordon. They studied, and finally Lovejoy in 2003. He has really brought this overpartition theory into the picture. So, and what is regular overpartition? It is the number of overpartitions of n with parts not divisible by L. Okay, so It's the number of overpartitions. So we have this overpartition. Then you count the numbers which are actually not divisible by that particular L that you have chosen. It's L regular overpartition. So if you look at this 4, you can see it's 10. So the if you take so a 3 of 4, so your L is 3 here. So these 3 things go away, and this 3 is here. This goes away. So out of 14, 4 goes away. So this is 10. This was introduced by Lovejoy. And then lots of people have worked on this. Shen in 2016 proved that these 2, 3, 4 dissections of this general generating function when L is equal to 3, 4. So people went on studying this L regular overpartitions, and then Alanzi, Monagi, and Sellers. So people have studied this L regular overpartitions. And my co-author Ray and his advisor Rupam Burman, who must have spoken yesterday, proved an identity that A9 bar n is congruent to. So again, people have studied the congruence properties of this regular overpartition and discussed families of congruences modulo 4 of this A12 bar n. Not only 4, 4, 8, 16 of A4L, etc. And one of these results is this nice thing that if you have p bigger than or equal to 5 a prime, such that minus 2 by p, this symbol is minus 1. Then for all positive integers n, l, and alpha, we have this overpartition, regular overpartition with 4l here is congruent to 0 modulo 16. You can put j equals to 1 to up to p minus 1 in this the j which is appearing here, 4j plus 3p. Go again. Now there's a little bit of this more generalization there, and use a singular overpartition PKI bar n, introduced by George Andrews, that number of overpartitions of n in which no part is divisible by k, and only parts congruent to plus minus I mod k may be overlined. This is another generalization of the previous notions that I was talking about. So 3 regular overpartition is same as, so there is a relationship between the regular overpartition and the singular overpartition. So 3 regular overpartition is same as 3-1 singular overpartition, that can be checked. And Andrews in this paper in 2015 proved the following Ramanujan type congruences. So those 3 congruences that I showed, they're the similar type of study for any partition function which is generalized after that are called Ramanujan type congruences. So you can see 9n plus 3, 9n plus 6, they're all 0 mod 3. That was by George Andrews. Okay, so people have went on showing, since the time is kind of running away. So this Rupam Burman and Chiranjit Ray have done quite a lot of work in this area, and a lot of other people, as you can see there, studying the congruence properties of this singular overpartition, where after Andrews introduced them in 2015. Let me come to the report, that the work that I want to report. It is a joint work, as I told you, with Chiranjit Ray, and it has electronically now it has appeared in Ramanujan journal. I don't know whether in the paper form it has come out yet. So suppose L equals to this prime factorization is there for L, and there's the prime, so greater equal to 5. That's the restriction that we're putting. And pi to the power ai is bigger than equal to L. So all these things are bigger than equal to L. Then for every positive integer n, we can get this kind of a distribution, the density results for this this overpartition. So a bar L n congruent to 0 mod pi to the power j, this pi is, and I'm counting, taking n up to x, and when I divide it by x, this goes to this a bar Ln. This is almost, this is 1 in fact. This is the distribution of these overpartitions that we are talking about. The other people have also And if k is a fixed positive integer and p bigger than 3 is a prime number, then we have this, it's pi to the power j. So this is in particular for prime, we are studying at a p bar, and it's divisible by p power k, and then you take your limit to infinity divided by x, it's also 1. Yeah, so Dr. Ali, how much time do I have? Because there's this.
So 2 minutes more. You
Yeah,
start
so let me
3 minutes
just
late. So you may
skip
take
the proof and go to the next result. So this notation, so this again, the generating function has been used for the overpartition to prove it, just like other people, they did it. And I can show you that where this modular form comes into the picture. We can have a look at this bijlz, and this is this eta, this dedicated eta function is coming into the picture here. And one would like to show that this is the eta quotient impact, and then we'll have the level and weight will be defined by the result of 10 Ono that I was mentioning to. So, and then use the property of modular forms, some result of Sayre to get this distribution, the density result. Yeah, so this is the weight that comes up there. So bijl, which I was mentioning, is one can show that it is holomorphic at C over D if and only this particular condition is satisfied. That was the hard work here to show. And then one goes in and one can show that this bijlz, that particular eta quotient that we're showing in the previous slide. In fact, this is the weight that comes up, and 1152 times L is the level that comes up. And the character also one can write it down explicitly. Then one uses the result of Sayre, which tells you that, if you have, let A denote the subset of integer weight modular forms, take mk gamma naught n chi, and take A is any set whose Fourier coefficients are algebraic. That's in OK, whatever field you take in. The ring of algebraic integers in a number field K. And suppose that this is an ideal in OK, integral ideal, and if there has this Fourier expansion, then you want to see that, look at all those n's for which A of n is divisible by that ideal is big O of x over log x to the power alpha. So this is the result of famous result of Sayre, which will give us the results once we plug in that particular modular form that we have got in this result. So this, as we have said, that this is the weight of this bijl, and this is the level that we get it, and then put in similarly for the other function. And by using this result of Sayre, one can show that limit is 0. So that is about this distribution. And then we have studied in the same paper some the congruence properties and produced infinite families of this. This is an infinite family here, and we have studied this A5 bar, and we have found some congruence results like the previous authors, they have done it for this particular overpartitions. So again, since the time is really limited, so I cannot go into the proof. Just was giving you a little bit of idea of the proof. The paper is there in archive and researchgate and maybe online also now. People can have a look at it, and if there are any more queries or questions that can be passed on after this talk to either me or to Chiranjeev, sure he's there. Then let me again. Okay, so I'm not really going into the thing again using the generating function and some results of Hashchion and Seller that is used here to prove this congruence result. And a lemma of Bush-Bernd also was of use for us to prove that the congruence result in particular modulo H. And it's again the similar technique that was used previously by the other authors, but here one has to really get hold of that eta quotient and show that calculating the level and the weight is the work, and then follow the standard method that is being employed by the other authors. This is the same thing that we want to show, that we used a result of Bushburn to get this congruent result. So not going into the thing, so we can have some discussion about the yes, so there is another result of this multiplicative type, that multiplicative formula, that if so again a5 bar, we are looking at L equals to 5, and then this is a similar result that the comparing which the other authors did it. So let R be a non-negative integer such that P divides 4R plus 3. Then if you look at a5 bar, this 4P to the power K plus 1 N PR. So we see some examples also. So 4P to the power K. So this is this, and this is congruent to mod 8. So you subtract this to, it will divide that one. So where FP, this FP is minus 1 or plus 1 according to P is 37 mod 20 or 1119 mod 20. I don't know why this is. Yes, so thank you. But I'm really sorry because of the technical, glitches that was coming up maybe from my end here. So I'll be happy to, if there are a few queries or any suggestions.
So thank you, Professor Kalyan. We can allow one or two very quick questions if there are any.
Yes, already, because the time is really.
If there are any question, you please can unmute yourself. Okay, if there is no question, then let's thanks the speaker for this nice lecture. Thank you, Professor Kalyan.
Thank you so much, sir.
The next speaker is Professor Shigeru Kanemitsu from Keishu Institute of Technology, Japan. He is speaking on zeta function and allied theta functions. So I'll request Professor Kanemitsu to start his talk. Professor Kanemitsu.
Yes. Let me. Can you see this? I hope. The
Yes.
slides are all right?
It is all visible.
Okay. So, good morning or good afternoon. I'd like to thank the organizers, especially Professor Ahmad Ali, Professor Patan, for inviting me to give a talk at this occasion. I wanted to attend this meeting in the last few years, but I couldn't because of bad timing. So I'm very happy to see you all of my friends, and I'm feeling family gathering, and this is joint work with Lee and Meta, and my talk is about reminiscence of Euler's identity. So here, the point is that we consider ramified Riemann-Hecke-Bochner correspondence, HB. This means that Hurwitz and theta functions satisfy ramified type function equations. And there are even an odd part is in RHB correspondence with a theta function and the conjugate theta function. It's a new aspect which I didn't know until I came to work on this. I mean, we come to one. And important part is probably that even zeta of s, the Riemann zeta function, is even part, but still we need both to get whole zeta of s. And the Euler identity reminiscence gives almost all known formulas in the theory of gamma and zeta functions. The other part is interesting, and this is the part which has been considered, studied by many authors. Like wherever you see the appearance of the Bernoulli polynomial, periodic Bernoulli polynomial, then it is even part, I mean odd part. Because this contains the partial fraction expansion of the cotangent function. So in many literature, most of the cases are considered odd part, which is whole minus even. So in our book, 2014, we were concerned with the equivalent expressions for the functional equation of the zeta functions. We didn't pay much attention to the counterpart objects of the RHB correspondence. Here we emphasize the counterpart, theta function-like stuff, and the transformation formulas for theta function-like functions, which are in the ramified RHB correspondence. And this governs the intrinsic nature of the corresponding theta functions. In some sense, this corresponds to consider the positive and negative integers with zero as a singularity. And it turns out that if I have time, I'll tell you that the Riemann famous proof of the functional equation using the theta transformation is indeed half sum, and it is the Ewald expansion. And I'd like to thank Professor Henhak Chan from Singapore. And this is his inspirational book on theta and elliptic functions that motivated us to make this research. Very recent. And especially I was inspired by his book. And Jacobi introduced 4 theta functions, and our main concern is theta 3. So this is theta. When I write theta, it means theta sub 3 tau x, which is an even function. This is a common notation. Q is equal to e to the pi I tau. This is a notation by Weber, and tau lies in H, the upper half plane, the Lobachevsky plane. So the change of variable gives rise to, x equal to tau over I. So it's better to see this table here, right? There are 3 objects, positive real axis. This is a part of right half plane. And here's the Lobachevsky plane. And here you see. This is zeta symmetry, and it's missing, but here we have a transformation formula. And in control theory, this is differential equation. And this corresponds to, on the Laplace transform, the transfer function. And on the upper plane, this is the Ziegler modular forms. So in terms of objects, then this is sigma and zeta functions and Lambert series in the upper half plane. So this is the correspondence. In case of the Riemann zeta function, there is a pole at s equal to 1. Therefore, the half plane, right half plane is restricted to sigma bigger than 1. So these are this is the case of Hecke correspondence. We have modular form, then the corresponding zeta function lives here. And also the Lambert series is here. And this circle itself is important because on this circle, the large zeta function is itself a Fourier series. The point is that theta functions satisfy theta transformation formula here. So this describes the behavior under the action of modular group SL to Z. And especially this spiegelung tau into -1 over tau is important. This is essential because these two, this translation generate this SL to Z gamma of 1. It is often the case that, especially in analytic number theory, is the case that is considered go to 0. It's just this. So this satisfies function transformation formula. This is the Jacobi triple product, and this is a starting point for our interest. By chance, we were reading the paper of Andrew Ogg, in which he proved this triple product formula using the theory of Riemann-Hecke-Bochner correspondence. This is a special case. This is Jacobi. So this is a Riemann zeta function defined in additive form. And this is continued analytically over the whole plane. And this vertical strip between 0 and 1 is essential. To go into this critical strip, you need Euler product, not just this. And here's the function equation, S to 1 minus S. As I said, critical strip is essential, sigma less than 1. Euler product is this. The Euler product is a very special, this is an expression for another expression of the unique factorization property. Not all the zeta functions have this Euler product, like epsilon zeta function have no Euler product. It's Riemann. So the passage from André is quite interesting. The relation between modular forms and Euler series with functional equations. So this was discovered by, actually rediscovered by Hecke, and brought out completely new aspect of the theory. So we refer to this Riemann-Hecke RHB correspondence. And this was coined by Marvin Knopp. So the origin is from this unique paper of Riemann. Then Hecke wrote a few papers and one book, Lectures on the Euler series. And this über die Bestimmung der Eulerischen Reihen durch ihre Funktionengreifung had a great impact on the research, and there appeared many papers. And Revey also wrote a paper. with almost the same title, but with the plural form, functional Gleichungen. And then Bockner made a decisive contribution to this, some properties of modular relations, this Hecke. So RHB correspondence means the correspondence under the Marian transform pair, these guys. And if you put t equal to nx, for instance, then we have n to the minus s here, and we call this to memorize Hecke gamma transform. Here it is, Hecke gamma transform. So this is Riemann proof we just recalled. Riemann used the theta function. Actually, he used this one, positive part, even part. But then transformation formula reads this, right? And then Riemann divides the integral into two parts. And Riemann's method turns out to be the Iver's expansion, which means the expansion with incomplete gamma function coefficients. It is developed by Lavrik and later by Terras. And this is chapter 5 in our book. So this is a table by Sato. Riemann, I already mentioned, generalizations, Hecke functions with Gresson character. Then comes Dedekind. But we found that between these, Riemann and Dedekind, there should be Hurwitz-Rausch zeta functions. So up here, up till now, it was considered that Hurwitz zeta function, their zeta function do not belong to this class of zeta functions whose function equations follow from the theta transformation. So define let L sub x be the boundary L theta function. It has a counterpart Hurwitz zeta function. They both reduce to the Riemann zeta function. And they are related by the Hurwitz formula, that is the function equation for the Hurwitz zeta function. It's reciprocal with this. But it turns out that these are better ones because they are Fourier series. And whenever you have this Hurwitz zeta function, it's better to replace by LSX, by L zeta function. The limiting case is this. And we remarked that Laurent constant is plus psi x, gamma prime over gamma. Another limiting case is this. So you see a strange relationship between these two, but they are very natural consequences of the coming our theorem, new theorem. And we refer to the Hutchinson paper long time ago. He considered these two even part and odd part. So we use ordinary notation like this, then f is f even plus f odd plus divided by 2. So now even part reads this. This even part, which means this one, is in RHB correspondence. But this does not lead to the function equation of the Riemann zeta function because we cannot put x equal 1 here. The odd part is this, is RHB correspondence with the transformation formula for the conjugate theta function. This is the interesting part. this odd part is important because it contains the partial fraction expansion for the cotangent function here. And it is in the long run, this is equivalent to the function equation. The definition is this. We say that phi, psi 1, psi 2 satisfy the ramified function equation in this sense, if this holds. So I already mentioned this, right? So theorem is this. The origin of the function equation, the Riemann zeta function, lies in the union of even and odd part. This is what we need. This means this one is 1/2. This is even part. This is odd part. If we put x equal to 1, this just cancel, disappears, and we have just this. But still we need this to get to recover zeta of s. So just rewriting these with the factor, pi factor here. Then we get the function equation, ramified function equation. And the corollary one is about Kumara's Fourier series. This is a consequence. And also Bernoulli polynomial, periodic Bernoulli polynomial, Clausen functions. These are all the consequences. So all these are the same. And this kind of thing is not a consequence of the function equation. This is the consequence of the structure of the periodic Dirichlet series. So I just show Aug's proof. Okay, so this is a Mellin transform, right? This must be subtracted so that this is convergent at the lower limit. So Aug has proved by Hecke's theory the function equation is in RHB correspondence. So here F1 is this one, F2 is this one. And here, to accommodate in Hecke theory, to accommodate the Riemann zeta function in Hecke theory, one needs to have a square. So anyway, we have this one. This is n plus x, 0 is excluded. So this is just even part. And to the even part, there corresponds even part of their zeta function. But important point is that to consider zeta of 2s, right? Then we are considering n squared, not n. So what we are considering is indeed a unary quadratic form, n squares. So the more important point is the corresponding theta function, the conjugate theta function. It's just this. This is a differentiated. If we differentiate theta by z and multiply by z, then we get this one. This is a conjugate theta function. And of course, we can read off this form from the function equation because it is in RHB correspondence. And we can also read this off, but we can also check that this definition, when we found this, we were thinking that this is a new thing, but it turns out that this theta function, conjugate theta function, appears in the work of Duravalev's-son, 1898, I think. And now it's in book form, even in the book form. So the conjugate theta function satisfies the transformation formula, and it is in RHB correspondence with the odd part of the Hurwitz theta function. And I'm afraid I'm running out of time. Actually, this is section 1 of our paper. And I just mentioned what are contained in the paper. Section 2 is about Dirichlet series with periodic coefficients, because a long time ago we came to this function equation through the work of Schunet in around 1930. Therefore, we went back to our old study and clarify the situation with the Dirichlet series with periodic coefficients. Then we focus our attention on the use of the Fourier Bessel expansion. This means the part of Dirichlet series, that is like zeta over Sx is part of the Dirichlet series. And this is in correspondence, in a sense, RHB correspondence with the K-Bessel series. And it is the main subject of Selberg and Chawla. And we call it Selberg-Chawla integral formula. But the most famous Chawla-Selberg formula should be named Lerch-Chawla-Selberg formula, which is rather peculiar because it connects the values at a rational point of two functions, theta function or eta function and gamma function. We made clear why such a thing could happen. And if you remove gamma function, then it is just like RHB correspondence between theta and processed by one-time function equation and the counterpart which is not processed. And finally, in section 3, we take up the famous Ziegler proof of the Hamburger theorem, that it is just another form of Fourier Bessel expansion, which is it is a variant of Watson formula around 1930s. And this is all I have used all my time. And I'd like to thank the audience and organizers. And let's hope to see you next year. Thanks a lot. Thank you. This is the Professor Ahmad. I'm done.
So thank you, Professor Kanemitsu. Are there any questions? I think there is no question. Thank you, Professor Kanemitsu, for this nice lecture. And our next speaker in this session is Professor Mahadeva Naika from Bangalore University, and he is speaking on restricted JK partitions. So, Professor Naika. Professor Naika, you can. Professor Naika, can you?
Yeah.
Yeah, please.
I had some problem in joining.
Okay. You can share your screen.
Are you seeing my screen?
Yeah, we can see you, but to start your presentation, you can share your screen. We already granted you the permission.
Yeah.
You have to open your slides.
I open the slides,
Yeah.
but
Share a screen option.
no, I'm not getting.
At the bottom, you can see one share screen option.
No, I'm not seeing that one. Okay.
In the Zoom window, at the bottom,
Okay.
you have share screen option.
Already,
Papa?
here I could not able to share.
So, did you
I
see
don't know.
the share screen button at the bottom of the Zoom window?
No. That is the.
It should be there. So, in the meantime, you try to find it, and you can log out on and then log in again.
Yeah. That's what I'm doing.
May I request the next speaker? May I request the next speaker so that Professor Naika settles his technical issues, and he will stop after this. So
Okay.
I will request Professor Hjalmar Rosengren. He is from University of Gothenburg, and he is speaking
Hello?
on Kanade-Russell identities. So,
Yes.
Professor, yeah, please.
Yeah, so let's see if I can share my screen then.
So, Naika, in the meantime, you can settle this technical issues.
Okay, so can you see my screen now?
Yeah, very well. Perfect.
Okay, great. Yeah, so first I would like to thank the organizers for the kind invitation to this meeting. So I really enjoy being here. So the title is slightly misleading because there's lots of Kanade-Russell identities. But I decided to just show you one in this talk and focus on that one. So now okay. So the plan is I will first say something about the Rogers-Ramanujan identities, which somehow lie behind the Kanade-Russell identities. And then I mention the Kanade-Russell identities. And then I will describe some approach to proving some of these identities. And these are multiple series identities. So that's two steps. First step, I reduce them to single series. And in the second step, I study these single series using Rogers polynomials. So the Rogers-Ramanujan identities we have seen several times. So I hope you agree that, I mean, they are wonderful identities, and it's maybe worth seeing them more than once in a meeting. So this standard notation, I guess more than half the speakers have used it, so I don't have to say so much about it. So the Rogers-Ramanujan identities is this pair of identities relating an infinite series and an infinite product. So you see here q to some quadratic power and some q analog of the factorial. And on the right-hand side, it has something to do with 5. So these have to do with congruences modulo 5. So these identities were first proved by Rogers, and then Ramanujan rediscovered them, and eventually they wrote a paper together on these identities. And they have a nice combinatorial interpretation that I think has also been mentioned, but I recall it. So it's easiest for the product side. So if you take the product side of the first Rogers-Ramanujan identities, you should you have all these factors in the product. So the exponents here are all integers congruent to 1 or 4 mod 5. And then if you expand each of these factors as a geometric series, and then you imagine multiplying all these things together, then to create a power q to the n, you have to pick some multiple of 1, here's some multiple of 6, and so on, some multiple of 4. So in effect, you're writing n as a sum of numbers that are congruent to 1 or 4 mod 5. So the coefficient here is counting the number of partitions of n into parts congruent to 1 or 4 mod 5. And the sum side, you need a little bit of work that I don't go into here. But you can show that for the sum side, the corresponding coefficient counts the number of partitions of n without repeated or consecutive parts. So therefore, those two numbers must be the same. And of course, that's quite a deep result. There's no obvious reason why those two enumeration problems should have anything to do with each other. And I want to mention that another reason people are interested in these things are connections to Lee Algebras. So you don't need to know anything about Lee Algebras here. I just mentioned it for history. So that Lepowski and Milne realized that the original Rogers-Ramanujan identities can be written as character identities for the affine Lee algebra related to the root system A11. So this is like the simplest example in of affine Lee algebras that are certain infinite dimensional Lee algebras. And then a lot of people have been working on these kind of connections. But just one I mentioned is that Misra found another interpretation of these identities using instead the A72 affine Lee algebra. And that I think was really the motivation for Kanade-Russell. So they studied the affine Lee algebra connected to the root system A92. And using that, they could conjecture several new Rogers-Ramanujan type identities. And then looking at the structure of these identities, they guessed that there could be more. So they also did some computer search. And with this computer search, they found even more conjectures that are not directly related to Lee algebras, as far as people know now. So what are those identities? Well, there's quite a lot of them. I think it's maybe 20 or so, but 9 of them give product formulas for special values of this type of triple series. So this might look complicated, but you see it has the same structure as the Rogers-Ramanujan identities. You have in the denominator these Q analogs of factorials, but here you have 3 different bases. You have Q to the 4, and Q to the 6. And in the numerator, you have some quadratic expression in the summation indices. And then I have here 3 power series variables that I could specialize. So what they found was that if you specialize those in 9 different ways, you get some explicit product formula for the sum. And as I said in this talk, I would just focus on one of them. So if you specialize the variables to q to the cube, q to the 5, and q to the 12, you get this product formula that seems very similar to the Rogers-Ramanujan identities, but you have the modulus 12 here instead of 5. And this particular one, it doesn't, that was found by a computer search, so it doesn't have a known direct relation to Lee Algebras. But all the Kanade-Russell identities have some combinatorial interpretation. So I want to go into that. So I have this identity. So as before, the right-hand side is very simple. So for the right-hand side, you can see immediately that counts the number of partitions of n into parts that are congruent to 3, 4, 5, 7, or 11 mod 12. And the sum side is more complicated, and I don't go into the details. But it turns out that you can prove that the coefficients in the sum side, they count the number of partitions of n that avoid some patterns. So I put quotation marks because I'm not sure what's the appropriate terminology really. But I think you will see by examples what I mean. So I said it avoids the pattern JJ. So if J is a part, it can't occur again. In other words, all the parts are distinct, just as we had before. It also avoids the pattern 2J, 2J plus 1. So it means that if you have 2 consecutive parts, then the smallest part can't be even. But you can have consecutive pairs where the smallest part is odd. That's allowed. And then it also avoids some patterns of length 3. So you're not allowed to have 3 consecutive even parts. Now, if you have 2 consecutive parts, then the smallest one has to be odd. And then you're not allowed to use the next larger even part. And similarly, you're not allowed to use the next smaller odd part. And finally, 1 and 2 are not allowed. So the smallest part you're allowed to use is 3. So that might seem quite complicated, but I mean, it is what it is. That's what these coefficients count. But in some sense, it's not so, it's similar to the Rogers-Ramanujan identity. So for the one we had before, that avoided basically J and J plus 1. So here you have something slightly more general where you also avoid some patterns of length 3. But it's not quite a natural as a generalization of the Rogers-Ramanujan identities. Okay, so here's, I think you have seen already, you have seen several pictures of Ramanujan, and I think someone showed Rogers as well. So here's Kanade and Russell. So what's known about these identities? Well, Brinkman, Jennings, Schaffer, and Malberg, in a paper which I think will appear soon, proved 5 of those 9 evaluations that I mentioned. And I got interested in this, and I found, I would say, a more streamlined approach that proves what they did, but actually I could prove all 9 identities in this approach. And for the 4 new cases, it turns out that the Rogers polynomials, so that's the same Rogers, play an important role in the proof. So that's what I want to describe in this talk. So here's a picture of the people who were involved in the proofs of 5 of the Kanade-Russell identities. So as I said, the first part in this proof is to reduce the triple series to single series. And for that, I need an integral representation. So here's again the definition of this triple series F. And I claim it's the same as this contour integral, where you basically you integrate around 0, and you have to be close enough to 0 so that all the poles are outside. And you might notice that that's actually an essential singularity at the origin. So you always have that inside the contour of integration. And this is actually very easy to prove. I have written this here as a product of 4 factors, 1, 2, 3, 4. And each of those 4 factors has a known power series expansion. So you basically just plug in the power series expansion and see what you get. So that's what I do here. So those 2 factors in the denominator, you can expand by a very well-known identity of Euler. That's one of Euler's Q exponential functions. That one is the other Euler Q exponential function. That one is Jacobi's triple product that Professor Kanemitsu just showed us. So if you plug in those expansions, you get the quadruple sum. You have all these things as coefficients. And then you just integrate a monomial. And of course, then the integration picks out just the constant term, where L is I plus 2j plus 3k. So you usually plug in that here instead of the L. So that's this quadratic exponent you had in the definition of the function f. So if you do that, you just get back the definition of the function f. So this is not so strange. It's pretty straightforward. And the next step is somehow to do something with these integrals. And for that, I need an integral representation of the function 2 phi 1. So the 2 phi 1, that's a straightforward Q analog of Gauss hypergeometric function defined by this series. And I claim that this function has a very nice integral representation like this. And I was quite surprised that I couldn't find this in the literature anywhere. Even though very similar integrals have been studied, I couldn't find this. So this, I think, is something that should have more general interest. So actually, the right-hand side displays all the symmetries of this function, and it also gives the analytic continuation outside the region of convergence. Okay, so I have this. So let me just sketch the proof of this integral representation. So to prove that, I introduce another factor here into the integrand. So somehow, I mean, it's quite typical when you study Q series that you want balanced things. So you have those 3 guys correspond to the 3 guys down here, but then you need something to match the one in the numerator. So it's natural to introduce this extra factor. And after you do that, you have introduced a sequence of poles at these points, p times q to the j, where j tends to infinity. So then you shrink the contour of integration and pick up the residues at all these poles. And if you have some conditions of the parameters, the integral is actually equal to the convergent sum of these residues. And if you write down that sum, it will be not a 2 phi 1, but a 3 phi 2 series. Then you want to let d tend to 0 to get rid of this factor. And you can't do that directly. You have to first apply a known transformation formula for 3 phi 2. Then you can let d tend to 0 and you recover the 2 phi 1. So that's the proof of this integral representation. And then you want to compare these to integrals. So in general, they are different, but for some special values, you can identify them. So for instance, if you plug in the values of the triple series in this way, some number u times q square and u cube times q cube, then you can check that the integral representation of that one is the same as the integral representation for this particular 2 phi 1 series. And here omega is a primitive cubic root of unity. And then what I want to do was to evaluate the function f of q cube, q5, q to the 12. You see, you get that if you plug in here u as q to the cube. So then what you want to do is to evaluate the corresponding 2 phi 1 series. Excuse me. And if you work out what the right-hand side should be, it's this thing. And then, I mean, normally I would think that if you have reduced yourself to evaluating at 251, then you're probably done. You just look it up in a book. But it turns out that this evaluation seems not to be in the literature. And it seems that it's not, I don't see how to derive it easily from known results about 251s. So I need to find some new approach. And that's where these Rogers polynomials come in. So that's the last part of the talk. So let me just, yeah, I'm doing fine with the time. Okay, so the Rogers polynomials, so they actually appear in the same series of papers where Rogers found the Rogers-Ramanujan identities. They are sometimes called the continuous Q ultraspherical polynomials. They are actually orthogonal polynomials, but I don't go into that right now. So there are some polynomials in a variable x of degree n, depending on q and another parameter a. And they could be defined in various ways. So for me, a convenient way to define them is through this generating function. So you take this simple infinite product and expand it as a series of in t. Then the coefficient is a polynomial in cosine theta, which is this Rogers polynomial. And I need to use another generating function for the same polynomials. So I claim that this 251 function, that's also a generating function for the Rogers polynomials. You just have some other factor here. And you see that this has a quadratic nature because this polynomial is in base q square, but the 251 is actually in base q. And as you might guess, this is related to quadratic transformations, in this case between Rogers polynomials and some other polynomials known as Askew-Wilson polynomials. So Ismail and Wilson found generating functions for Askew-Wilson polynomials. So if you use those generating functions and use this quadratic transformation, then you can easily derive this alternative generating function for Rogers polynomials. So as I said before, now someone is drawing on my screen. So I'm reduced to computing this 251 series. And you see that this is something that could appear here as a generating function. It has the same structure. So to identify this function with this generating function, you should replace q by q to 1/2. You should put, this is a cubic root of unity, so theta should be 2 pi over 3, and yeah, a should be q to the 3/4, and t should be q to 1/2. So we have the generating function with some special choice of all the parameters. So I don't know how to remove these things. Someone, I don't know if you see it, but someone draws something on my screen. But yeah, I hope it's not too disturbing for you. Okay, so what you should notice is this choice. You have theta is 2 to the 2 pi over 3. So this was the second generating function, but I want to use also the first generating function. So I plug that special value into the first generating function, and then I get this identity. And this thing, when object is a cubic root of unity, you can rewrite in this way. So basically, if you have 1 minus t omega times 1 minus t omega square, you write it as 1 minus t cubed divided by 1 minus t. And you do that for all the factors inside this infinite product. And then this right-hand side, you can expand by the Q binomial theorem. And you get this type of series times this type of series. And then you can identify the term here corresponding to t to the n. And that gives you an expression for the Rogers polynomials, which is only valid at this special point. Okay, so this is minus 1/2, as you know, but I wrote it like that. So it's some kind of cubic identity for Rogers polynomials at a special point. And that I will use. So what I do is that I plug in this expression for the Rogers polynomials into the second generating function. So then I have some double sum. I change the order of summation, and then it turns out you can compute both the inner sum and the outer sum using this classical Q-Gauss summation. And then eventually you arrive at what you get. You prove the Kanade-Russell conjecture for these special values, Q cubed, Q5, Q to the 12. And as I said, Kanade-Russell conjecture, 9 evaluations of this triple series. And all of them you can prove in the same way. And it turns out that the 5 cases that Brinkman, Jennings, Schaffer, and Malberg could do, they're all easier because the single series you get you can compute by simpler means. You don't need these Rogers polynomials. So this is one of the new cases. And the other 3 new cases, they are a little bit more tricky, but not so bad. So what I showed you was the simplest case that was not known before. So for the other ones, I mean, sometimes the parameters are a bit off, so you need to apply some contiguous relation, something like it. But it's the essential IDs are the same. You just have to modify them by some pretty simple tricks. And this I mentioned because it could be interesting to some of you that. So what I did before was that I specialized both T and A. You could get something more general by letting T and A satisfy just some relation like that. And then if I do the same thing, I can't sum the series completely, but I get instead of a summation, get a transformation formula. And I get this quite nice sextic transformation, which I think is new. So you see here is base Q and base Q to the 6. So some sextic transformations exist in the literature, but not so many. So again, if I then choose A is Q to the 3/4, then the right-hand side becomes summable. And I get this summable 251 that proves this particular Kanade-Russell conjecture. So in some sense, this is more general than the Kanade-Russell identity, or it's like a source of that result. Yes, I'm almost done with my talk. So I want to mention that I can also do some other things with the same methods. For instance, I can get a very easy proof of a partition identity that was conjectured by Caparelli, and that also came from Lee Algebras, and that was first proved by Andrews. And I can get some new results that could be interesting to some of you. For instance, I mean, just by very slight variations of what I do, I get this triple sum. And here you see it in the one I had before, I had the basis here, Q square and Q to the 6. Here I have instead Q minus Q and Q to the 6. Otherwise, it looks quite similar to the Kanade-Russell identity. And the right-hand side is really nice. So that's a series in Q to the 2, and the coefficients, of course, count just the number of partitions of n into parts that are not divisible by 6. So a question that maybe some of you are interested in is, what does the left-hand side count? I don't know, but I mean, I know some people in the audience are very clever with these kind of things. So maybe they can tell me what. I mean, if this is a Rogers-Ramanujan identity, what does it mean combinatorially? So I have some more things similar to that. But I want to stress that what I have described it's not like a universal method. There's lots of Rogers-Ramanujan type identities known, and certainly most of them can't be proved by this method I have. Some of them can, but for others you need other methods. Okay, so if you want to read more than this, the paper I have on this is on the archive, and it will appear in the Ramanujan journal. So that's all I wanted to say. Thank you.
So thank you, Professor. I'm sorry, someone has created this disturbance. So are there any questions?
Professor, I have a small doubt regarding your slides.
Yes.
It is in slide number 16. You have mentioned some integral.
Yes, I should share it again. Sorry.
It's a basic question, actually. I just wanted to know what will be the convergence of this integral, or how we can check the convergence of this type of integrals.
Yeah, it's very easy. I mean, so this type of integral, it's considered in the book by Gasper and Riemann. They have a section exactly of this kind of integrals. So now I don't remember the region of convergence in my head, but in my paper I write it very clearly when it converges, and so.
Okay. Thank you.
So it's. I mean, I have considered this question, and it's no problem with the convergence here.
Okay.
But of course, certainly you need some condition on this D, on the parameters for this to converge. Yeah. Thanks for pointing this out. I should have been more clear, I think. Yeah.
So thank you, Professor, for this nice talk. The next speaker is Professor Mahadeva Naika from Bangalore University, and he is speaking on restricted JK partitions. I hope, yeah, Professor Naika. Yes,
Yeah.
perfect.
Now it is okay?
Yeah.
Screen is okay?
Yes, it is all okay.
Okay. So I would like to thank the organizers for giving me an opportunity to share some of the things which I have recently found, these results. So today I'm going to talk on restricted JK partitions. So let us start with the definition of the Ramanujan theta function. So already many people have defined this f of AB as in 1. So this theta function is defined by Ramanujan in his chapter 16. So all the results in chapter 16 were proved by Adiga, Bart, Bhargava, and Watson in the following paper. So special cases of these functions are phi of q. So it is as in 2, and xi of q, it is as in 3. And moreover, because they have already explained these entities, because phi of q generates the squares and xi of q generates the triangular numbers, and f of minus q, it is famous pentagonal numbers. So, and I'm also using the another famous identity as in 6. So let us start with the brief history of the Leibniz appears to be the first person to consider the partitioning of integers into sums, and Euler was the first person to make truly deep discoveries. So next, the person is Sylvester was the next researcher who made major contributions. And 20th century saw an explosion of research with monumental contributions from Rogers, Hardy, McMahon, and Ramanujan, Regimeters, and many more mathematicians. So in 1674 letter, Leibniz asked Bernoulli about the number of partitions of integers. He observed that there are 3 partitions of 3, 2 plus 1, and 1 plus 1 plus 1, where 2 plus 1 and 1 plus 1 are the same, and 5 of 4. And he went on, observed that there are 7 partitions of 5 and 11 of 6. So, this question comes to his mind, whether the number of partitions of any n might always be a prime number. The answer is no, because the P7 is 15. So, are there infinitely many integers n for which the total number of partitions of n is prime number? So, it is still an open problem. So, Euler was asked in a letter from Noida to solve the problem of partitioning of a given integer n into given number of parts. So, for example, there are 2 partitions of 5 with number of 2 distinct parts. 4 plus 1 and 3 plus 2. So similarly, Noida asked how many partitions there are of 50 into 7 distinct parts. So this question was posed to the Euler to solve, because the correct answer is 522. So the author thought that this could not be found by writing all the partitions of 50 and calculating them. So there must be some formula to find out this. To give answer to his Noida's question, Euler considered this summation d of m comma n, z power m, q power n. Here summation m comma n equals 0 to infinity. So here m is missing. In the right hand side, we are considering 1 plus zq times 1 plus zq square, etc. The product. So the right hand side product generates the number of partitions of n into distinct parts and m distinct parts. So after the first factor, you put z equals zq equals t. So and compare with the above product. So one in place of z we are having t. So if you write in a place of this one and simplify this and comparing the coefficients of z power m, q power n on both sides, we are getting this recurrence relation. By using this recurrence relation, Euler was able to solve the problem of Noida. So, for example, n equals 10 if the number of partitions of 10 into 2 distinct parts. So, d 2 comma 10 equals d 2 comma 8 plus d 1 comma 8. So, again you apply for 2 8, we are getting d of 2 comma 6 and d of 1 comma 6 and 1 8. Now, we can easily solve this by because the number of partition of 1 8 is 8 only, so therefore it is 1. So we are getting the total is 4. So these are the 4 partitions of 10 into 2 distinct parts. So Euler was naturally led from Noida's question to even fundamental one. He find the generating function for P of n. He considered this series and this product is product 1 plus q power n plus q power n plus n, etc. So because mod q, he took mod q less than 1, therefore this becomes a product 1 over q1 minus q power n. Then this can be written as 1 over q infinity. So that means the Euler gave a generating function for the number of partitions of n. So the formal definition, as you know, the partition of a positive integer n is an odd increasing sequence of positive integers whose sum is n. So this is the generating function, summation n from 0 to infinity, p of n, q power n equals 1 over q infinity. If we expand this, we are getting 1 plus q plus 2q square plus etc. So the coefficients gives you the number of partitions of n. So, in these two, the following papers, Ramanujan also announced that he had found 3 simple congruences satisfied by P of n, namely P of 5n plus 4 congruent to 0 mod 5 and P of 7n plus 5 congruent to 0 mod 7 and P of 11n plus 6 congruent to 0 mod 11. So, by seeing the table established by McMahon, by using the recurrence relation, he found the number of partitions of n equals up to 200. By seeing the table, Ramanujan is able to conjecture the following. That means P of 4, 9, etc. They are all multiples of 5. The number of partitions of P4, P9, etc. They are all multiples of 5, and similarly this. After this, Ramanujan has formulated the following conjecture as a P delta n plus lambda congruent to 0 mod delta, where delta is 5 power a, 7 power b times 11 power c, and lambda is an integer with 24 times lambda congruent to 1 mod delta. So Gupta extended this table up to n equals 300. By examining the Gupta's table in 1934, Chawla found that P of 243 is not divisible by 7 cube, despite the fact 24 times 243 is congruent to 1 mod 7 cube. So then Chawla corrected Ramanujan's conjecture. So Ramanujan also found the generating function for P of 5n plus 4 as in 14. So RD states that if I had to select one formula from all Ramanujan's work, I would agree with McMahon in selecting the formula 14. So this is simplest generating function for P of 5n plus 4 cube. So now we are defining the irregular partition. A partition of a positive integer n is a irregular partition. None of the parts are divisible by n, where L is a positive integer greater than 1. So for a generating function is summation n from 0 to infinity BL of n q power n equals q power L infinity divided by q infinity. Now if B L equals 3, it is called 3 regular partitions. So we are getting this, and if you expand this, we are getting this 1 plus q plus 2 q square, etc. Plus 2 q cube, because here the 3 regular part B3 of 3 is 2. So 3 we are not considering because it is divisible by 3. 2 plus 1, 1 plus 1. So this is the 3 regular partitions of 7. So in the following paper, Kalkin et al. Have examined 5 regular partitions modulo 2 and 13 regular modulo 2 and 3 using modular forms. Ishon and Seller in the following paper, they have more stronger, they have used results, obtained a more stronger results for 5 regular partitions by using Jacobi triple product identity. So in the following paper, Q and Gu have derived several infinite families of congruences modulo 2 for L regular partitions, L equals 2, 4, 5, 8, 13, 16. So bipartition of a positive integer n is a pair of partitions lambda mu such that the sum of parts equals n, where mu, lambda and mu are allowed to be empty partition also. So this is the generating function. So it is denoted by P of minus 2 of n, q power n equals 1 over q infinity whole square. So we are getting this. For example, there are 5 bipartitions of 2, namely 0, 2, 2, 0, 0, 1 plus 1, 1 plus 1, 0, 1, 1. These are the 5 bipartitions of. Now, in the following papers, Atkin and Ramanujan have established the Ramanujan type congruences for bipartitions. So L regular bipartition. So L regular bipartition of a positive integer n is an ordered pair of L regular partitions K1, K2 such that the sum of all of the parts equals n. So this is the generating function as in 19. Now the following papers, Lin and Dow and myself and Hemant Kumar obtained results for L regular partitions. So many mathematicians have obtained several infinite family of congruences satisfied by BL of n. So now we have defined JK partitions for a positive integer j and k such that k greater than j greater than or equal to 1. A partition of n is JK partition of n if none of the parts are congruent to j modulo k. So the generating for it is denoted by Pjk of n, denoted number of such partitions of n, and the generating function summation n from 0 to infinity Pj k of n q power n equals q power j q power k infinity divided by q infinity. Now suppose here if j equals k equals L, then it turned out to be L regular partition. So if you slightly change the definition of the irregular partitions, if none of the parts are congruent to L modulo L, then we will get this. So if none of the parts are congruent to L modulo L, then it becomes L regular partitions. So the mathematicians have studied regular partitions, but they have neglected the case where L is not equal here, J is not equal to K. So now we consider the J is not equal to K. For example, 5, 10 partitions of 5 are 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, etc. 2 plus 1 plus 1, all ones. So these are the 5, 10 partitions of phi. So in the following paper, myself and Professor and Harish Kumar and Veerana have found the JK bipartitions of K. For positive integers J and K, such that J greater than K greater than J greater than or equal to 1, a bipartition of N is an JK bipartitions of N. None of the parts are congruent to J modulo K. So the generating function as in 21. So now here all the mathematicians earlier have studied when the case J equals K equals L. So now we can take if J is not equal to K, other cases of we can study the congruence properties when J is not equal to K. So for example, 3, 6 bipartitions of 3 are 8, 2 plus 1, 0, 2, 0, 2 plus 1, 2, 1, 1, 2, 1 plus 1, 1, 1, 1 plus 1, 1 plus 1 plus 1, 0, 0, 1 plus 1 plus 1. So these are the infinite families of congruences we obtained in that paper. So in the following paper, Andrews, Epstein and Sellers have considered the function P E D of n. That means the number of partitions of an integer n with even part distinct. The odd parts are unrestricted. So for the generating function as in 22. So they obtained infinite family of congruences. These congruences for 23 and 24. Many mathematicians obtained infinite families of congruences for PD of n. So in the following paper, they obtained the congruence modulo 2 and 4 for PD of n. And Naika also obtained some results for PD of n. So Lin also obtained. So Dai has also obtained some results for and myself and my student Harish Kumar, we obtained 5 regular bipartitions with one part distinct. So these are the results we obtained. So in the paper, we defined JK partitions into even part distinct. So we defined the function PDE JK J, K of n, the number of JK partitions of a positive integer n into even part distinct, where none of the parts are congruent to J mod K. So here, the generating function is as in 25. So for example, 3, 6 partitions of 7 into distinct parts are 8. So 7, 6 plus 1, 5 plus 2, 5 plus 1 plus 1, 4 plus 2 plus 1, 4 plus 1 plus 1 plus 1, and 2 plus 1 plus 1 plus 1 plus 1 plus 1, and 1. So we obtained these infinite family of congruences, modulo 16. And in the following paper, we define the partition function BPD J, K of n. That means the number of JK bipartitions of a positive integer n with even part distinct, where none of the parts are congruent to J modulo K. So similarly, we obtained many infinite family of congruences. Next, the partitions with odd parts distinct. So already in the following paper, considered the function POD of n. That means the number of partitions of an integer n with odd part distinct. Here, even parts are unrestricted. Epstein and Sellers have obtained infinite family of congruences for POD of n. And Rado and Sellers have studied and they obtained the congruences modulo 5 and 7. And Girish, Irshan and myself, we obtained the arithmetic properties of 3 regular non-multiples of 3 in which the odd parts are distinct. We also obtained the internal congruences tested by Hjalmar Kumar and myself. We have obtained the 9 regular partitions with even part distinct. Here, these are the results we obtained. In the following paper, Chen and Lee defined POD minus 2 of n. That means the number of bipartitions with odd part distinct. They established Ramanujan type identities. and myself and Harish Kumar, we obtained the following, established many infinite families of congruences modulo powers of 2 for 5 regular bipartitions with odd part distinct. So myself and my student, we obtained in the following paper, we obtained established many infinite families of congruences modulo power 4, 5 regular bipartitions with odd parts distinct. So in the following paper, myself and Harish and Virnaik, we considered the partition function POD j, k of n, the number of jk partitions of a positive integer n with odd part distinct, where none of the parts are congruent to j mod k. So the generating function for this is as in 29. So for example, 3, 6 partitions of 7 with odd part distinct are 7, 6 plus 1, 5 plus 2, here 5 plus 1 plus 1 we cannot take because the odd parts are repeating. So 4 plus 2 plus 1, 2 plus 2 plus 2 plus 1. So even parts, we are not putting restriction on even parts, but odd parts must be distinct. So we established many infinite families of congruences modulo powers of 2 for POD 3, 6 of n and POD 5, 10 of n, modulo congruence modulo powers of 2 and 3. And so over partitions, in the following paper, Cartil and Lovejoy, they laid out the groundwork for flourishing new component of the theory of partition called over partition. So over partition of a non-negative integer n is an increasing sequence of natural numbers whose sum is n, in which the first occurrence of a number may be overlined. It is denoted by p bar of n with the following generating function. So here the summation n from 0 to infinity p bar of n q power n equals minus q infinity divided by q infinity. Here 1 over q infinity, naturally it generates the number of partitions of n. So we are adding more partitions to it. So minus q infinity is the generating function for the number of partitions into distinct parts. So we are adding the distinct parts to the generating function. So that means we are getting more partitions. So that's why they may call it as over partition. So if we expand this, we are getting this. So for example, there are 8 over partitions of 3, 3 bar, 2 plus 1, 2 bar plus 1, 2 plus 1 bar, 2 bar plus 1 bar, 1 plus 1 plus 1, 1 bar plus 1 plus 1. So in the following paper, the author proved p bar of n is divisible by 2 power 6 for almost all positive integers n. So in the previous lectures, the Kalyan Chakraborty has explained all these things here. So the Kim proved for k equals 7. This. So Ishan and Sellers, they have also proved find the arithmetic properties. They have proved arithmetic properties expressed by p bar of n and obtained many Ramanujan type congruences modulo powers of 2. So myself in the following paper, we established several infinite family of congruences modulo powers of 2 and 3 for 2 color over partitions. So myself and Shiv Shankar, in the following, we proved that the Ramanujan like congruences and infinite family of congruences modulo 3, 8, 16, 36, 48, 96 for 3 regular over partition pairs and modulo 3, 16, 64, 96 for 4 regular over partition pairs. In the following paper, Adiga, Naika and Rangnath and Shiv Shankar, we proved several infinite families of congruences modulo 8 for 2k regular over partitions. And Sumant, Hemant and myself, in the following paper, we obtained many infinite family of congruences. Myself and Harish, we obtained 5 regular, established many infinite families of congruences modulo powers of 2 for 5 regular partitions of n with the first occurrence of an odd number overlaid. So in the following paper, we obtained 4, 5 regular over partitions. So next, jk over partitions. For positive integers, j and k subject k greater than j greater than equal to 1 and jk over partitions of n. If partition of n in which the first occurrence of each distinct part congruent to J modulo K may be overlaid. So here, let P bar J comma K of n denote the number of such partitions of n with P bar J is 1 and generating function is this. So what is here? If J equals K equals 1, we are get back to the over partition. So which the Andrews already defined by Andrews. So this is 5 comma 10 over partitions of n, 5 bar 4 plus 1, 3 plus 2, etc. So these are the over partitions of n is a JK over regular over partitions, none of the parts congruent to J modulo K. So P bar J comma K of n denote the number of such partitions of n with P bar J comma K 0 of 1. So this is the generating function. This is the example for 3 comma 6 regular over partitions of 3 are 2 plus 1, 2 bar plus 1, 2 plus 1 bar, 1, 2 bar plus 1 bar, 1 plus 1 plus 1, 1 bar plus 1 plus 1. So here in this following paper, we obtained infinite families of congruences for the next the JK regular over partitions. This is the generating function. So we obtained infinite families of congruences for modulo powers of 2 and 3. So in JK over partitions with even part distinct. So this is the we introduced the J here then it is not the we have considered the function PD bar of J comma K of n, the number of JK over partitions of positive integer with even part distinct, and the first occurrence of each distinct part congruent to J modulo K may be overlaid. So this is the generating function. So we obtained many congruences for this. So in the following paper, so we considered POD bar of J comma n, the number of JK over partitions of a positive integer n with odd parts distinct, and the first occurrence of each distinct part congruent to J modulo K may be overlaid. So this is the generating function. We established infinite families of congruences similar to the Ramanujan-like congruences. So cubic partition. So cubic partition of a positive integer n is a partition in which the even parts appears in 2 colors. So the cubic partition of 3 are 3, 2 suffix 1 plus 1, 2 suffix 2 plus 1, suffix indicates the color, 1 plus 1 plus 1. So this is established by, studied by Chan, and Chan obtained the following congruences. So this congruence is similar to the Ramanujan one. So, and Chan Tau obtained many, I proved the powers of analogous to Ramanujan type congruence for A of n. So Girish, myself obtained in this paper we give affirmative answer to Chan's question by finding alpha beta L such that B of 3 power alpha n plus L congruent 0 mod 3 power beta. In the process we also alternative proofs for Lin's conjecture. So we obtained in this paper we established some infinite families of congruences modulo 4 B2 of n, and Girish, Shivshankar and myself we obtained the following congruences modulo powers of 3 for large power of 3. So these are the results we obtained for cubic partitions. So in the following paper, we define A, J, 2J of n. So we took the generating function as in 40. So this is 3, 6 cubic partitions of 4 are the following, and we obtained these are the results we obtained. So with this, that was the Riemann notation. That was the wonderful thing about Ramanujan. He discovered so much, and yet he left so much more in his garden for the other people to discover. In the 44 years since that happy day, I have intermittently been coming back to the Ramanujan's garden. Every time when I come back, I find fresh flowers blooming. So with this notation, I conclude my talk. Thank you Yeah, one and all. And again, once again, I thank the Ahmad Ali for giving me an opportunity, sharing some of the things with audience. Thank you, one and all.
So thank you, Professor Naika. Uh, are there some questions? Are there any questions? I think there is no question. Then let's thank the speaker, Professor Naika. Thank you very much.
Thank you very much.
Exciting lecture.
Okay, thank you.
Yeah, and so we have come to an end of this session, and I once again thanks all the speakers for their enlightening lectures, and our next session, which is the last session of invited talks, session 6, will begin at 2 p.m. Indian time, and we have two speakers in this session. They are Nayandi Barwa from Tejpur University, India, and Jeremy Lovejoy from Seine University of Paris, France. So I hope that everyone will join us again at 2 p.m. in the next session. So thank you very much for your presence here. Thank you and all.